So in this lecture, we will see the investigation of design parameters for a subsurface drainage system. There are three design parameters: drainable porosity, water table, and hydraulic conductivity. Both of the first two we have seen in last lecture. So we will see hydraulic conductivity today. So hydraulic conductivity, you all know what is hydraulic conductivity. So the principle of drainage is Darcy's law. You all know that. So while deriving the Darcy's law, you know that V is equal to Ki. It is Darcy's law. Okay. So in that, K is the coefficient used. Darcy's law states that the velocity of flow of water is directly proportional to hydraulic gradient. For removing the coefficient, for removing the proportionality sign, we have given a coefficient which is K. That K is known as hydraulic conductivity. It is actually the measure of rate of flow of water through the soil. K is the measure of rate of water, how fast the water will move through the soil, how easily the water will move through the soil. That is K. So K can be of unsaturated soil and saturated. Okay, so unsaturated means when all the soil pores are filled with water, what is the rate of movement of water? That is saturated K. When all the soil pores are not filled with water, that condition is known as unsaturated condition, and the movement of water through that kind of soil is known as unsaturated hydraulic conductivity. Okay, so there are two types of K, unsaturated and saturated K. So we will see the saturated K, saturated hydraulic conductivity, because we are dealing with drainage. So we will see the saturated condition, how the water is moving through the soil. Okay. It is otherwise known as, the hydraulic conductivity is otherwise known as coefficient of permeability. It also varies with temperature. The K value varies with temperature, and this here there is an equation which shows the change of K with temperature. So its relation, it is related to temperature as well as viscosity. So here we can see that K20 is equal to mu T divided by mu 20 into KT, where T is the temperature at T degrees Celsius and 20 is the temperature at 20 degrees Celsius. Okay. Mu is the viscosity. Mu T is the viscosity at temperature T, and mu 20 is the viscosity at temperature 20 degrees Celsius. So for finding the hydraulic conductivity at 20 degrees Celsius, we have to calculate this equation. Okay. So this is the relationship between hydraulic conductivity, temperature, and viscosity. Now, for determining the hydraulic conductivity, there are mainly two methods. One is correlation method and the other one is hydraulic method. And this hydraulic method is again divided into two: laboratory method and field method. So correlation, from this name itself you can see that it is a relation between two parameters. So correlation, there will be an equation connecting the hydraulic conductivity to some other parameter. So using that equation we will find the K value. That is known as correlation method, a relation between two parameters. Hydraulic method means we will measure the hydraulic conductivity by using some instruments or some methods or something. So here in this method you will use some equation, a direct equation will be there. You will use that equation for measuring hydraulic conductivity. In this method you will use some instruments or some methods. Okay. Hydraulic methods are of again two types: laboratory and field method or in situ method. Field method is otherwise known as in situ, I-N-S-I-T-U, in situ method. So we will see each of them. First one is the correlation method. As I have explained earlier, it is based on a predetermined relationship between an easily determined soil property. It may be texture, pore size distribution, grain size distribution, etc., and the hydraulic conductivity. So we will have an equation between hydraulic conductivity and any of these parameters. By using that equation we will find hydraulic conductivity. So that is correlation method. So here we can see an example of a correlation method. It is Hazen formula. It is an example of a correlation method for finding hydraulic conductivity. So this is Hazen formula. K is equal to A D10 square. D10 is nothing but it is the effective grain diameter. So here you can see the relation between hydraulic conductivity and grain size diameter. So this is a direct formula. You can find K by using this formula if the D10 value is available. A is a constant which is usually taken as 1. Okay. So you can easily find the hydraulic conductivity. So this is about correlation method. It has some advantages and disadvantages. Its advantages, it is a very easy method and it's a simpler method. Nothing, we have to do nothing. We have an equation, we have to just substitute the values to the equation for finding the k value. But its drawback is it is not accurate all the time. It is just an equation. Okay, this equation will be derived for some places or some type of soil. So it cannot be applicable for all types or all situations. Okay, so that is the disadvantage. Now we will move on to the next method. It is hydraulic method. In hydraulic method there are many methods. So seeing this, it is you may think that it may be difficult. No, it will be following the same procedure. All that method will be following somewhat same procedure. We have to just remember that method only, that procedure only. Okay, so hydraulic methods are mainly divided into two methods. One is laboratory method and the other one is field method. Field method is otherwise known as in situ method. Okay, laboratory method, you may have heard of these two, constant head permeameter and falling head permeameter method. These two are the laboratory methods. And in field method, there are mainly two. One is small scale and the other one is large scale. Small scale method are again divided into two, infiltration and extraction method. Infiltration methods are of four types: shallow well pump-in method, Guelph permeameter method, inverse auger hole method, cylinder permeameter method. And extraction method are of two, auger hole method and piezometer method. And large scale method are of two, pumping test and parallel trains method. So we will see each of them, but you don't worry that you have to study this much. Okay, all the methods will follow some procedure. Okay, the same procedure they will follow, a slight differences will be there. Okay, that's the only thing. So don't worry about this. We will easily study this. Okay. So this slide shows the normal values of K for saturated soil. Hydraulic conductivity values for saturated soil. This is a normal value. For generally we can say that between 100 and 1 it will be clean gravel. It will be between 1 and 0.01 centimeter per, the unit of K is centimeter per second, centimeter per day or meter per day. Okay, it will be meter or length per time unit. Okay. For clay, it will be very less. It will be less than 0.0001 centimeter per second, like that. So clay value, for clay the hydraulic conductivity will be very less, and for a large sized particle or coarse textured soil the K value will be higher. So this is about the K values, and we will move on to each of the methods. So hydraulic methods, we will move on to hydraulic methods. Hydraulic methods is mainly based on imposing certain flow conditions in the soil and applying an appropriate formula based on Darcy's law and the boundary condition of the soil. So in this method, other than when comparing to the correlation method, hydraulic method will have a certain procedure, will have a certain equipment or device to measure the hydraulic conductivity. That is the difference between hydraulic and correlation method. Okay. So there are two types, laboratory and field methods. We will see each of them. So we'll see the laboratory method first. In laboratory method there are two types, constant head permeameter method and falling head permeameter method. We will explain this by means of a figure. So this is the figure for a constant head permeameter. It is a hydraulic method which is used in laboratory for finding K value, saturated hydraulic conductivity value. So you can see this figure. This figure is a setup for constant head permeameter. So here you can see this is an undisturbed soil column which is placed in a cylinder shaped container. Okay. So this is the soil column. Above and below the soil column there will be a permeable strata. There will be a permeable layer. It may be some net shaped, it may be some cloth or net or something. Okay. So which sustains the soil in the cylinder. Okay. Above this there will be a tube which will be supplying water to this soil sample. So here there is a tube or some provision for providing water. And there are two tubes at the upper end of the soil and at the lower end of the soil for showing the head of water. How much amount of water is present in this layer, it will be shown in this tube. Okay. And at the bottom there will be another tube which carries the excess amount of water to the container. This is a graduated container. Okay, so this is the setup for a constant head permeameter method. In this, what we are doing is we will place the soil sample here. The length of the soil sample is L. It is a cylinder shaped soil sample and its length is L. Okay, it is placed in between two permeable layers. Here we will supply the water. We will supply the water in such a way that the head between these two pipes will be constant. That is, this H value will be constant, have to be constant. Okay, we will supply water in such a way that this H value is constant. Okay, so when we supply water, what will happen? This water will flow through the soil sample and it will be delivered at this end because we are placing permeable layers here. These two are permeable layers, so the water will flow through the soil sample. It will be delivered to this graduated pipe. Okay, and the amount of water collected here will be measured in by using this jar. That amount is Q. That Q is we can directly measure that Q value, and the time taken for collecting that much of water will also be noted by using some stopwatch or whatever it is. And we can find K by using this equation. K is equal to Q into L divided by A into H into T. A is the area of cross section of the soil specimen. So area of this portion. This will be a circle because it is a cylindrical shape. So the area of cross section will be this area. It will be a constant. You can measure it directly. H is the head maintained here. So it is a constant head. T is the time taken for collecting this much of water. And L is the length of the soil column. So all that parameters you know, then you can find K value. So this is how we will use constant head permeameter method. This method is mainly used for coarse textured soil. Large sized particle soil, we will use this method. For example, gravels or sand particles, we will use this method because it will allow more water through it. Okay, so we have to continuously supply the water for maintaining a constant head. So this is about constant head permeameter method. Hope this is clear for you. If you have any doubt, you can ask me in the last of the section. Next one is falling head permeameter method. There will be a slight difference. Setup will be the same. Setup will be same as constant head. Here you can see this is the setup for falling head permeameter method. Here we will place the soil column here as in the earlier case. This will be a cylinder and we will have a permeable layers at the bottom and top of this soil column. There will be a tube or standing pipe above this through which we can supply water. And at the bottom there will be another tube through which the water is collected at this end. Okay. In this case, we will supply the water up to this level. Okay. First we will supply the water up to this level. After that we will not supply any water. Okay. We will provide the water up to this level only. H1 is the initial level of water. After that we will stop supplying water. We will not supply the water. Okay. Now what will happen? The water will infiltrate into the soil and it will reach here at this end. Okay. And above this the water will be overflow. Okay. So this is the constant, this is a constant level of water, and above this the water will be overflow. So initially the water level was H1. So at this point the water will be there. So this is the H1. And after some time, so at T1 the water level was H1, and after some time at T2 the water level will be H2. Okay, so like that we will not supply extra water. We will supply the water to this level at the initial stage. After that we will stop supplying the water and we will measure the change in head. So that is the case of falling head permeameter. In constant head permeameter method, we will continuously supply water. In this case, we will not continuously supply the water. And the head will not be a constant. Here, the head will be changing. Initially, it was H1 and finally it was H2. The change in head is measured here. And we will use this equation. Here, the velocity can be measured by dH by dt, the change in head per unit time. And the flow into the sample, the water flown into the sample, that is here, the water flown into the sample is through this pipe. So that is equal to A into dH by dt, area of this pipe into change in head per time. That is the amount of water flown into the sample. Amount of water flown out of the sample is represented by Darcy's law. It is equal to K into I into A. I is equal to H by L. H is the change in head and L is the length of the sample. It is not represented here. L is the length of the sample. Into A is the area of cross section of this pipe. Area of cross section of this pipe. It is a circular area again. And the Q in is equal to Q out. You all know that. Amount of water passing into this pipe or into the soil sample will be equal to the amount of water passing out of this sample. So Q in is equal to Q out. So you can equate these two equations. Okay. And you can integrate these two equations for finding the K value. We are integrating it using the limits T1, T2 and H1, H2. And after integration, we will get this equation. AL divided by A delta T into ln H1 by H2. So 1 by H is equal to log H1 by H2. So we will get a log. And finally, we will get the equation K is equal to 2.303 AL divided by A delta T log H1 by H2. This 2.303 is came after converting this logarithm, this natural logarithm into log to the base 10. When we are converting natural logarithm into log to the base 10, we have to multiply it with 2.303. So this will be the equation for finding K using falling head permeameter method. Hope it is clear for you. If it is not clear, this equation you have to write once and you have to derive it. Okay. So this is a simple equation. So this is about the laboratory methods. Now we will move on to the field methods. In field methods are of two types, small scale method and large scale method. Small scale method is again divided into infiltration and extraction method. In infiltration method, they are the methods used to determine K above the water table. Infiltration methods are used to find the saturated hydraulic conductivity above the water table. Okay. And in this method, there are steady state method as well as unsteady state method. We will see each of them. In the steady state method, what we are doing, you all know that what is infiltration? Infiltration is the movement of water into the soil. Okay, rate of movement of water into the soil. So we will measure that for finding K value. So that it is known as infiltration method. While the other method is extraction method. Extraction method is the amount of water we are extracting from the soil. We are taking water out of the soil and we are measuring the rate at which the water is taken out of the soil. So that it is known as extraction method. So there are two types of small scale method, infiltration method and extraction method. Okay, another one is extraction method. In infiltration method, we will measure the amount of water moved into the soil, while in extraction method, we will measure the amount of water coming out of the soil. Okay. That is the difference between these two methods. The infiltration method are of steady state as well as unsteady state are there. In the steady state, what we are doing is, we will continuously apply the water to the hole. We will make a hole and we will continuously apply the water to the hole. Okay. So when water is applied continuously, first what happens is, the surrounding soil will be saturated with water. Okay. After saturating the soil, what will happen? Again the water will move down the soil. After saturating the soil, again the water will move down the soil. Okay. That rate we will measure. That rate of water we will measure using some instruments or some equations or like that. Okay, so that is steady state method. In that method, we will continuously apply the water, as in case of constant head permeameter method. We will continuously apply water to the soil. We will maintain a constant head of water above the soil and we will measure the rate of decrease of water. So that is steady state method. In case of unsteady state method, it is similar to that of falling head permeameter method. We will not give continuously water. Continuous supply of water will not be there. We will just give some amount of water and we will measure the rate of decrease of water afterwards. Okay, that is the difference between steady and unsteady method. In steady state method, where there are shallow well pumping method, Guelph permeameter method, and in unsteady state method, there are inverse auger hole method and cylinder permeameter method are there. So we will see each of them. First one is shallow well pumping method. From this slide onwards, it is very easy for you. The procedure will be same, but slight differences will be there. So first method is shallow well pumping method. So you know that what is infiltration. Infiltration is the movement of water into the soil. So we will measure that infiltration rate for finding K value. Okay. So shallow well pumping method is a steady state method. So we'll maintain a constant head of water over the hole. First, in this method is found by Gulver and Sanger in 1956. It is not important for you. This is the procedure for shallow well pumping method. First, we will make a shallow hole in the ground above the water table, and we will maintain a constant head of water above the water table. We will pour some water into the hole and we will maintain a constant head by applying continuously the same amount of water. Okay, we'll maintain a constant head above the hole. The hole is saturated until a steady state condition is reached. First, what happens is when water is poured into the hole, first the hole will be saturated. The surrounding soil will be saturated. Okay. After that, after saturation, the water will be moving in a steady state. With time, it will be constantly moving with the same rate. Okay. That is steady state. And the rate of infiltration is then noted. After this equilibrium is reached, the rate of infiltration is noted. Okay, a constant head is maintained during the measurement of data. So this is about shallow well pumping method. We are making a hole, we are pouring water into it. First the water will saturate the soil. After that the movement of water into the soil is measured. While taking measurements, the hole should have a constant amount of water. We will maintain a constant amount of water by continuously applying water. This is about shallow well pumping method. This is the figure for that. So this is the shallow hole having a diameter 2r. The constant head of water maintained inside the hole is y. So we will maintain the y amount of water above the hole. This is the water table. We are making hole above the water table. And the infiltration rate is measured after saturation of the soil. So this will be the equation used for finding the K value here. This is a derived equation by some scientists. Okay, so this equation is used for finding the amount of K value. Okay. And this we'll move on to the second method. Second method is Guelph permeameter method. It is similar to that of shallow well pumping method. It is also a steady state method. It is also an infiltration method. So we will see the procedure for that. First we will make a hole. The hole will be having a depth of 15 to 75 centimeter. It is made below the soil surface above the water table. And we will add water to the hole. First the hole is saturated until a steady state condition is reached. Now the Guelph permeameter, it is an instrument. It is a portable instrument. It is inserted into the hole for measuring the rate of water into the soil. Okay, influx of water into the soil. We will see the figure and I'll show you. First what we will do is, we will make a hole. This is the hole having a diameter 2h. And we will pour water into the hole. H, capital H is the amount of water, constant amount of water which is applied into the soil. Continuously we will apply water into the soil for maintaining this head. Okay. First what will happen is, the surrounding soils will be saturated. After that a constant amount of water will be moved into the soil, or a constant amount of water will be infiltrated into the soil. After that we will insert this permeameter, Guelph permeameter. This instrument is known as Guelph permeameter. This end of this Guelph permeameter will have a graduation. Will have graduation just like scale. Okay. So the amount of water moving down will be measured by using this Guelph permeameter. The influx of water will be measured by using this Guelph permeameter. It will have a graduation for measuring the amount of water moving down. We will maintain a constant head here, but the amount of water, the rate or speed of water will be measured by using this instrument. Okay. So this is a portable instrument. Okay. By using this equation, we will find the K value. So this is also a derived equation which is derived by some scientist. So CQ divided by 2 pi h square. H is the constant height of water, plus C pi A square. A is the radius of this hole. C can again be calculated by using this equation. C is a constant. It is known as Glover's constant. This equation is known as Glover's equation. Okay. By using this, you can find the K value. So these two were the steady state methods in infiltration method. And another, the third method is inverse auger hole method. This is an unsteady state method. Unsteady state method. So it is otherwise known as Porchet method. Inverse auger hole method is otherwise known as Porchet method. So why it is known as an unsteady state method? So this is the procedure. We can see the procedure and we can see what is the difference between these methods and the other two methods. Okay. A hole is dug in the soil surface. Okay, this is same as above. Water is allowed to infiltrate into the soil around the hole. Yes, of course. We will dig a hole and we will pour some water into the hole, and water is allowed to infiltrate into the soil around the hole. Now the hole is saturated until a steady state condition is reached. After saturation point is reached, rate of declination of water table at different times will be calculated. Okay, so in this procedure, what we are doing is, we will first apply some water. For example, in this figure, we will apply Y1 amount of water in the hole. We will make a hole having 2R diameter and we will apply Y1 amount of water. Okay, we will allow the water to infiltrate into the soil. We will not provide extra water. Okay, we are not continuously providing water. We will provide, initially we will provide Y1 amount of water. After that, we will measure the decline of water. We will measure the decline of water. After some time, what will happen is the Y1 amount of water is decreased to Y2. Okay, all the amount of water will be infiltrated into the soil. This infiltration of water will be measured. This rate of declination of water will be measured, and we will find the hydraulic conductivity by using this equation. Okay, so this is also a derived equation. K is equal to R by 2. T2 minus T1 is the two time periods, and ln y1 and y2 are the two heads. Okay, after time. R is the radius of this hole. So this is the unsteady state method, inverse Auger Hall method. Another unsteady state method is cylinder permeameter method. This is similar to that of inverse Auger Hall method. A large diameter hole is dug in the soil. A steel cylinder will be inserted into the hole, which is having 50 centimeter diameter, and the hole will be larger. The cylinder will be having 50 centimeter diameter. So there will be an annular space between the cylinder and the hole. Okay. So between these two, between the annular space, we will place two tensiometers. We will place two tensiometers in opposite directions between the annular surface of the cylinder and the hole. Okay. And it is placed up to a depth of 20 centimeter. Water is ponded into the cylinder. Up to a 15 centimeter depth, water will be provided in the cylinder. And after that, the rate of decrease of water in the cylinder will be measured. And by using this equation, we will find the hydraulic conductivity. K is the hydraulic conductivity here. V is the infiltration rate that we can measure from this experiment. Z is the depth of the transmission zone, total depth of the zone. Phi is the suction at the bottom. This suction will be carried out or measured by means of gravimetric method. That is not necessary for you now, but this is a suction. H is the height of water in the cylinder. So this is a procedure for cylinder permeameter method. So with this, we have finished the infiltration methods. Now we will move on to the extraction methods. How can we measure the hydraulic conductivity by means of extraction? So up to this, we were discussing about infiltration, the movement of water into the soil, measuring hydraulic conductivity by the movement of water into the soil. Now what we are doing is, we are extracting the water out of the soil and we are measuring the hydraulic conductivity. So it is known as extraction method. So in this method, there are two types, Auger Hall method and piezometric method are there. Okay. It mainly measures the horizontal hydraulic conductivity. Okay. We will see the Auger Hall method. The principle of this method is to measure hydraulic conductivity by measuring the rate of rise of water in the hole. Earlier it was the rate of decline of water or decrease in water. In this case, it is the rate of rise of water because we are extracting water. So we will measure the rate of rise of water, and all these extraction methods are below water table methods. We will dig the hole below the water table. Earlier, we have dug the hole above the water table. Okay, so these are the two differences between these two, infiltration and extraction method. In infiltration method, we will dig hole above the water table and we will infiltrate the water. In extraction method, we will dig the hole below the water table and we will extract the water. Okay, this method is found out by Desarin in 1934, and we will see this method. A hole is bored into the soil to a certain depth below the water table. Water equilibrium is, so when we dig a hole below the water table, what will happen? Water will come from the soil. It is just like digging a well. Okay. So when a hole is dug below the water table, water will come from the soil. Okay. That is the condition. So water will come out of this hole. When equilibrium is reached with surrounding groundwater, a part of water in the hole is removed. So some part of the water which is coming from the hole is removed by means of pumping. Okay. After some times, we will measure the rate at which the water rises in the hole. Okay, after pumping. So the pumping is done for making the water into equilibrium with the groundwater. Okay, pumping is just a procedure for making the water into equilibrium. After pumping, the rate of rise of water will be measured. This rate of rise of water is converted by a suitable formula for measuring the hydraulic conductivity. So this is the procedure used in extraction method. So this is a figure. Here we will dig the water, dig the hole below the water table. This is the water table. So we will dig the hole. Just like a well, we will dig the hole below the water table. It has a diameter of 2r. What will happen? The water will rise in this hole. We will pump out some amount of water and we will then measure the rate of rise of water. Okay, so this is the method. All the quantities are given here and we will use mostly the horizontal hydraulic conductivity is measured by using this formula, and this method is limited to areas with a high groundwater table. With a high groundwater table only we can use this method, and this method can be used for, it is not suitable for layered soils. This method is not suitable for layered soil. Different kinds of soils are there, then this method is not used. We will use the Hoogout's equation. Hoogout's equation, it is an equation derived by Hoogout for finding the hydraulic conductivity of the soil. We will use the Hoogout equation for calculating the hydraulic conductivity of the soil. Actually, in this case, in Auger hole method, we will use Hoogout equation. So here I have given the derivation for Hoogout equation. This is your practical session. I will discuss in the practical session. Actually, the derivation of this equation I will discuss in practical session. We will see the final equation. Okay, finally the Hoogout equation will be K is equal to 523,000 into R square. R is the radius of the hole into log y0 by y1. Y0 is the initial level of water in the hole. Y1 is the final level of water into 1 by delta t. Delta t is the change in time for change in this head. Y0 to y1, how much time is taken, that is delta t. So by using this equation we can find the K value. This equation is known as Hoogout equation. In it, K is found out by using meter per day, unit meter per day, and delta T is in second, and Y1 and Y0 are in meters. So this is the equation for finding K using Auger hole method. And the final method in extraction method is piezometer method. It is otherwise known as pipe cavity method. It is similar to that of this Auger hole method. An auger hole is made. Okay, in this case a hole is made and it has a cavity at the end. I will show you the figure, and a pipe is inserted into the hole. In this case we will insert a pipe. Okay, a non-perforated pipe is inserted into the hole, leaving only a small cavity at the bottom. Water can only flow through this cavity. After water comes to equilibrium, some amount of water is pumped out of this hole. After that, the rate at which the water will rise in the hole is measured. Okay, from this value the hydraulic conductivity is calculated. So it will give the vertical saturated hydraulic conductivity or horizontal hydraulic conductivity. When the length of the cavity is 0, the measure will be fully vertical. So we can see the figure. Here what we are doing is we will dig a hole and we will give a cavity here. This is a cavity. We will insert a pipe. So this is a pipe. This bold section shows a pipe. There will be a cavity below the pipe. Okay, water can flow through only this cavity and the water will enter into this pipe. We will pump out some amount of water. After reaching equilibrium, then the rise of flow in the water, rise of the water in this tube is measured. Okay. When this cavity, the length of this cavity is 0, it will give the vertical hydraulic conductivity. When the length of cavity is not 0, it will give the horizontal hydraulic conductivity. So that is the difference, and we can find K by using this equation where C is the shape factor. C is a constant known as the shape factor. It is different for different types of soil. It is already known value. And T2 and T1 are the time taken for the rise in water. Y1 and Y2 are the change in water level. R is the radius of this hole. So by using this equation, we can find the hydraulic conductivity. Why it is known as piezometer method? Because we are inserting a pipe or a piezometer into the hole. So it is known as a piezometer method. It is also an extraction method. So these are the different hydraulic methods used. And till now we were discussing about the small scale method. There are also large scale method. When a large area is there, how can we find the hydraulic conductivity? We can use two methods here. One is pumping test and the other one is parallel drains method. Pumping test method is nothing but we will construct a well, a large well we will construct, and we will use the pumping test. We will pump out the water and we will measure the hydraulic conductivity. Parallel drains method is nothing but we will use, there will be some drains in that area, and we will determine the hydraulic conductivity from the functioning of the drains. Okay, drainage systems. So these are the two methods which we are used in large scale for finding hydraulic conductivity by using hydraulic methods. So this is about today's lecture.